Here we go. We have a brief entry to topological fluid dynamics. Frozen fields will be important. And then conservation of magnetic and kinetic helicity. Helicity is an important quantity in this context. Then you will see the connection with the linking numbers. And I'll briefly mention today about topological change under reconnection processes that are prevented by frozen fields, and energy complexity relation, just to give you an idea of what was the work and what is going on right now, maybe. The plan of these lectures are that this is an entry to helicity and linking numbers. Then we will have tomorrow the second lecture on magnetic relaxation and tight knots and the connection with ideal knots. So we have a kind of connection between, or relationship between topology and global geometry. And then the third lecture will be focused on topological change under reconnections. And finally, following more or less the philosophy of knot theory, we leave behind linking numbers and we move to knot polynomials and up to, let's say, I want to talk about Vasiliev, we get to Jones, etc. But you see the idea that has been developed. Okay, so I'll be rather quick at the beginning. A brief entry to the origin of all this is well known to the experts, and it started with a number of people. I have a beautiful historical timeline of contributions I won't show you here, but imagine that we have Riemann and Gauss on the mathematical side at the beginning of topology, and on the applied side we have Helmholtz and in particular Kelvin. So actually Germany has a great important role in the founding topological field theory, so to speak. As I said, Gauss and Riemann on one hand, and Helmholtz and other in applied sense. Here, Kelvin knew about conservation laws of Helmholtz and immediately took the idea of the fact that these vortices could represent particles. So it's a string theory of 1860s. Strings of these vortices could be thought of as particles in microphysics and embedded in an ideal fluid, no reconnection, no change of topology, but the topological types of knotted vortices could justify the quantization of the energy that was already known from spectral theories or spectral experiments from chemists at the time. So that was the idea. Wow, we have quantized energy from laboratory work of chemists. Here I have a theory that justifies this quantization in terms of topology. For the time and even now, is extraordinary. So, of course, you can see Edwin's theory rooted in Kelvin's work. And here are the original sketches that I could photocopy and copy from the library of Cambridge University. And you see his idea, and there's even an exercise. The exercise is to do something starting from the parametric description of a trefoil knot. You see here the polar coordinates, x and r, and see what eventually could be done by those. He needed a knot theory because he wanted to establish connection between dynamical properties and topological properties. There was none done, so he asked his junior collaborator, long-term collaborator, Tate. Kelvin's name was Thomson and Tate T, so they were well known as a T and T prime as contributors to not only this theory, but they ended up to produce a series of books, actually only 2 printed. There was books fundamental for the education of generations of students in Britain, including my supervisor, Keith Moffat. He also studied on treatise on natural philosophy of T&T prime. Anyway, this is Tate, more or less the same age, and this picture representing him at that time. And this is the first knot table. You probably know very well about this, and with the interesting features already there. And this is the last work that he published. He went up to 10 crossing tabulations in 1885. And every few, let's say, every 8-10 years, he had the typical blues of a knot theorist, because you start classifying things, you see relations coming out, etc., etc. Think of alternating knots, you are very happy, and then at a certain point you go into the blue period where everything is not going the way you expect, and new rules emerge. And here is just a quick view of the contributions, main contributions. Maxwell was immediately extremely interested in contributing to this work. He never published anything, but it was so important to the work of Tate that Tate, in a private letter at a certain point in his first publication, he said, "You have to be a co-author." And we're in a different time here, and Maxwell said, no, the work has originated from your own ideas, you should be the only author. Different times. Okay, so topological fluid mechanics in a sense emerged as a first topological field theory, classical field theory. And here I want to give you a sense of so many ramifications in many directions. You see, not that solutions to Euler equations belong to the field of dynamical systems and rigorous mathematical search for a 3D fluid topology, were exact solutions in terms of topology of Euler equation, the role of invariance in fluid flows and the role of invariance in topology, and questions of stability, which are very, very modern aspects. Energy relaxation, which will be my lecture tomorrow, you will see starting from putting some, let's say, physically known energy, like magnetic energy, but then going to charge, not putting a charge and making this not electrically charged. If they are electrically charged, there is a repulsive force that, push them apart, push the strands apart as much as possible. If you prevent in self-intersection, so you confine topology, then they get to relax, so to speak, to an ideal form. But then again, the ground state energy question that triggered the interest of Kelvin, the ground state energy of relaxed magnetic or electric knots, and wild energies that came out of this work. Dynamical systems I mentioned already. Here we focus really on the technical meaning of dynamical systems. So existence theorem for vector fields, closed and chaotic orbits, Hamiltonian structures. I didn't add one theme that is a very modern and recent, is using let's say homological techniques to study these orbits. And then finally, we have a change of topology. If the fluid is real with reconnection, etc., then reconnection mechanism, what kind of mechanism we have, either in the vortex dynamic, in the magnetic field context, or quantum context, and the singularity formation, which is an open problem, one of the open problem of the Clay Institute. So is linked to this, is one big problem of singularity, existence and uniqueness of possible singularity emerging from Navier-Stokes equation, including now Euler equations as well. Okay, this is the state of the things. Here are just a few pictures of work being done. Here is quantum, I should say, topological field theory, relaxation of skyrmions. And then we have all this enormous work going on complex filamentary structures that are forming tangles in space, etc. And then the energy of magnetic loops, so to speak, with application in astrophysics and, of course, with application in plasma physics as well. Okay, the ideal fluid context, I will have 3 or 4 slides just to go through the basic theory. Again, here we have to at least, in my case, show some technical aspects of fluid mechanics. I apologize. I guess part of you don't know anything about this. I will be very brief, and Alice will take my stage to explain everything. So ideal, incompressible, and perfectly conducting, no neutral fluid, so to speak. We take R3, although we can extend this to higher dimension. U is the velocity field, X is the position vector, T is time. We take a solenoidal condition for U, meaning incompressibility. By the way, for everybody, you will see solenoidal field, divergence-less fields everywhere. Divergence free field for velocity, vorticity, magnetic field, potentials, and so on and so forth. So when you see this condition in annals of math paper, think of physics. Physics is relevant for physics as well. All right, so it's not sad, but this is the state of things. Frozen field evolution, it means that we have an equation here that you recognize as a Faraday's equation, with the assumption that div B, you see divergence-less on the field B, for example, magnetic field in this case, is 0. This is because there are no monopoles so far. And the equivalence, topological equivalence, is the following. You imagine that your magnetic field or vortex fields, etc., the field is localized in space and time, so it stays localized in tubes. Okay, we're moving to fluid knots, and if it stays in these tubes, we have the flow map that sends the initial position to the final position. So when you consider isotropy transformation, isotropy mappings better, of your knot to an equivalent knot, that is done here with time. So it's time is producing a movie instead of pictures of equivalent knots. And this is the innovative way to see topology here in this context. And under this equation and similar equation for vorticity, you have this Cauchy problem that was known at the time of Cauchy, that you establish an equivalence between the initial field and the final field through this deformation tensor. And evidently, we assume that everything is smooth. It admits inverses, and this is an issue for real fluids. Sometimes you have difficulties to do this, but if you admit that you can go one way and come back, then this is the way to get topological equivalence. Of course, this means this deformation tensor means that you can perform continuous deformation of the structures you have here. And of course, sometimes it's not true when you have a change of topology and you have a reconnection. But as long as you don't have cuts, then this is allowed. And evidently, you are establishing a topological equivalence between the initial field and the final configuration. So the exercise, the visual exercise for you, is to go from here to there or the other way around in a continuous way. And this is taken from Prazolov's book, a little book of AMS, long time ago, and this is a beautiful thing because it defies intuition clearly. And the way to sort it out is through continuous deformation. You have to stretch this tube. Imagine this is a dead stuff, okay? It's not vortex or magnetic. It's just something that you can deform, and you have to perform some twists inside, and by stretching and twisting, you reduce the first stage to the last stage or reversing. Okay, so this is, by the way, the twist, stretch, and fold mechanism plays a very important role in dynamo theory. And I've been advertising this to people working in geodynamo because they don't know about this. And this, for me, a very interesting aspect of research. Okay, we have helicity now. As Samuele showed you, we have the product of a field times the curl of a field. And the bad news for some of the experts, I went to Keith Moffat almost immediately after a month. I met him, I went to the library, and the good point of libraries, still now, is that you can find things that are not on internet. And one thing I found was that the product, the scalar or the inner product of a potential and say the curl of the potential, or better in differential form, A wedge dA, is in a paper by Whitehead, 1947, showing that this integral, A wedge dA, is an isotopy invariant. He had no ideas of application, etc. The paper was totally forgotten. And when people, in particular my supervisor, start to work on this, were 30 or 40 years later. Okay, so helicity is an important quantity. Here we have magnetic field instead of vorticity. So I will call it magnetic helicity. And we want to prove that this quantity is constant in space and time. So this is the work of Voltier. I present the derivation in my modern terms, and you find this derivation in a couple of books, not many books around. But anyway, this goes this way. The Faraday's induction is the starting point, is the equation I showed you at the very beginning, and then you uncurl it. So you go back to the potential A for the magnetic field. This is the result. You have to consider that emerges a gradient. Potential theory is a fantastic building block for topological fluid mechanics and topological field theory. So I encourage you to go back to potential theory, where many things emerge more clearly. Anyway, this phi is a scalar potential. You play a little bit with the solenoidal condition on B, and you multiply this A by B. You take the time derivative, A dot B, to get to this integrand, and then you work, the B times U cross B is hidden here by rearranging things, and then you have the B times the grad phi. Considering the B is solenoidal, you can rewrite this expression in this form, and then you play with vector identities a little bit, and by playing with vector identities, you come up with these two different contributions. You rewrite ddTAB plus the divergence of this quantity, and you write this in terms of this, and then you're ready, because you take this part and you plug it in at the beginning in the AB formula, and using Reynolds kinematic transport theorem, you can, by using this right-hand side form of the equation, you reduce it to this, you are done, because you have a divergence of something. And the divergence of something, I'm sorry, I skipped one detail on helicity. Here, you see, I'm assuming that these flux tubes have no flux through the tube of the magnetic field. The magnetic field is totally confined there. There is no transverse contribution. So because of that, you can apply the divergence theorem, and you get to this form by S. I mean the bounding surface of your tubular knot, and because there is no flux of the through the boundary of your tubular knot, then you are done. Okay, we have a second quantity similar to the first one, because the structure mathematically is identical, is the velocity in this case times the curl of the velocity, as we had before. So U here plays the role of A, the potential, but the formalism is identical, and you want to prove exactly the same. You assume that localized structures have no flux of vorticity through the surface bounding the tube, and in order to prove this, you go to different type of equation. Here, before we use the Faraday's equation. In this case, we use Euler equations, ideal fluid. This was done by Moreau, 1961. You notice one is 1958, Volcher, and Moreau, 61. Volcher published the paper in PNAS, Proceeding National Academy of Sciences, and USA, and Moreau in the Compte Rendu de l'Académie des Sciences de Paris, so is the equivalent for the United States proceedings. But he didn't know anything about Volcher's work. Not the time of internet and archiving papers, etc. And so the proof goes like this. You have to enter with the total derivative, noting that the domain of integration is basically a material domain. So you can split the derivative in two. For du dt, you use Euler equations, which are here, and for d omega dt, you use Helmholtz equation, which are basically these ones, and then you just go quickly to reduce this integrand to the divergence form. Again, you apply divergence Gauss theorem, and you get no flux of vorticity through the surface, so you get to this result. Here, I want to play the movie. Is done by William Irvine and I can't remember his name, Kleckner, in the laboratory in Chicago, and this is the first time they realized the production of a trefoil knot. That was one of the hopes of Kelvin to work with knotted vortices. Here the knotting, it's a little bit trick played, because the topology actually is already there, because they produce a trefoil knotted airfoil, and the topology actually is transferred to vorticity. I can show you how to produce a knot exactly the way Kelvin did, i.e. through starting from a trivial topology through interaction and producing a real a non-trivial topology. Anyway, we follow this work, which is remarkable. What you will see in white are the vapor bubbles, tiny bubbles released in the water, in fluid. And you see the realization, the production of a trefoil vortex filament, very thin, visualized by these air bubbles. Techniques used is amazing, is incredible. You see here, if there is a reconnection, a change of topology is a real fluid, and there are 2 or 3 stages where the topology changes, you can still follow it, and then, of course, dissipates. It's real fluid. I don't want to spend time on this because I want to talk about reconnections and changes of topology, so I go back to this movie. We have other types, of course, of research going on, not only an isolated thin vortex filament in water, but a complicated tangle of vortices in classical physics, but also in this case in superfluids and condensates. You see how complicated these things are going. This is already old of 10 years, and I don't want to update the slide because my point is to show you the progress that has been done during all these years. And then, of course, the study of entanglement, better to say the braiding of magnetic loops on the sun. Again and again, I can say, when I was your age, somebody said, well, these are not real braids. This is just an effect of the picture taken by satellites. Now, after so many years, you see already old of 24 years, now you go on internet and you see these braided solar loops very, very well. Is the efficiency and the observational results are so clear from satellite that definitely the energy is localized on flux tubes. I was, when I was more or less your age, a bit older, on the safe side, because I just came from talking with an expert in St. Andrews. His name's Roberts, I can't remember, Bernie Roberts, and he was just showed me a manuscript that went published in Nature, where the title was 90% of energy of all frequencies confined in flux tubes. So I was on the safe side, but I had to argue with people, say, well, energy is everywhere, and why flux tubes? And okay, so here I want to point out an analogy, because I mentioned vorticity and magnetic fields. So I want to show you that, remember vorticity, curl of velocity, divergence less. This is the equation, Helmholtz equation, that represent the form of Euler equation, and this is kinetic elasticity. Then I mentioned magnetic field in terms of the vector potential. There is an equation that resembles very clearly the Helmholtz equation, is the Faraday equation, and then we have magnetic helicity. The interesting thing is that this analogy is not exact. Yes, you can draw an analogy between vorticity and magnetic fields, but the difference is that this U is related to omega, so this is really a highly well-known non-linear differential equations, where here the velocity is totally unrelated to magnetic fields. To be clear, imagine that you have some flow here, you open a window, you have a wind coming from somewhere, and air is flowing, and imagine that you have a magnetic field from one corner to the other. The magnetic field may be transported, moved by the flow. So in this context, the magnetic field is like, some paper coffee powder that is transported by water to some extent, because it reacts back. So it's more complicated than this. So in this sense, it's a non-perfect analogy. Anyway, here we have the work of Keith Moffat, 1969. You remember that we come from this integral. So we have an integral, a volume integral, and after some work, you can show that this volume integral can be written in terms of these quantities, where phi, you think of phi as the strength of your vortex tube or magnetic tube, and SL, LK are here. LK is the Gauss linking number between components in the link, and SL is the self-linking number, so it's the topological corresponding quantity for knots. Okay, I'll be very quick on this, because I assume most of you know very well this. This is the formula. My way to look at this formula is very different from when I met this formula first time. Think of dx, dx1, dx2 as a surface, is a triple integral, as a surface, and a surface with one normal direction. So it's an elementary surface. And then you take this quantity, you divide by the mod 1, and so you have here a triple integral of a product of a unit normal, because you divide it by x1, x2 mod, unit normal time the surface with a unit vector, and there you have a square now. 4 pi r squared is the surface of a sphere of radius r. So you have a contribution of a spherical part here divided by a sphere. And what I'm talking about, solid angle. This is the solid angle. This is the solid angle. And of course, it's known to some people, but not so well known. Anyway, from the solid angle perspective, I want to stop. And I want you to imagine what's going on. Now you are at the center of a sphere, and around you, you have filaments. And imagine that these filaments half-link. And imagine that there is an intersection, let's say apparent crossing of the half-link, and nothing else around you. So evidently you have a half-link, you are at the center, you have two crossings, two apparent crossings, right? So you look at one, and there is a contribution from the triple product, because the two strands identify a non-zero contribution to the solid angle. but all the rest is empty except the other side, where you have the second apparent crossing from the Hofling. From this, in words, you can prove that by using sign convention that we use in standard knot theory, you can come up with reducing this complicated formula to this one by counting the signs of the crossings. I told you if you see a crossing, that counts +1, -1. If you don't see any crossing, it's 0. That's why you can reduce this integral to where the crossing you see are present. Okay, so you count the crossings. Now remember, the good point of this is this quantity is topological. It doesn't matter which projection you take. So if you have an off-link or whatever shape the Hofling has, not certainly the standard one, virtual or crossings, let's say, then they don't count towards the linking number obligation.
You talked about solid angle. What do you mean by solid angle?
Solid angle is defined. It's an old concept. So you take R, this is a unit vector, and you do this, ds. ds is just elementary surface given by this times a unit vector going out of the surface. Imagine that you have a contribution like this. To a point here. And this is part of a sphere, right? It's a part of a sphere. Okay, and then what you do is R square. And there is a 1 for pi here. Okay, you can remove this, put it inside, and you have this. My R is, this is the square of R. I don't put double bar. R is just x1 minus x2. Okay, and this is the solid angle omega. Okay, so now imagine that this strand going this way, this is x1, say, and this is, of course, is not correct, but you understand what I mean. This is a piece of x1, and maybe there is a piece, sorry, I'm just improvising, of the other curve, okay? This is x2, and the other piece is this. So what happens is that you see a piece here, x1, dx1, and here is a dx2. And so you interpret the crossing, the apparent crossing that you see from P, as a part of the contribution of this on the sphere, on the Gauss sphere. And so if you see a crossing, it contributes to +1, then there is maybe another one there that counts for 2, that's why you have a half, and then the rest you don't see any crossing at all. This is beautiful. This is what Gauss had in mind. Solid angle to interpret things in physics, but then he got to this expression. You know, this expression there is no demonstration of this expression. And the demonstration came from Maxwell. Maxwell understood what was behind the work of Gauss, because the work of Gauss, I read it, I can barely read German, because I studied German in school. I can't speak it, and I went through 60 pages of this work. Is on geodynamo theory, the first theory of geomagnetism on Earth. And he started considering the Earth and made by layer, and then so on and so forth. I have a paper, you can look at the paper, it doesn't matter. There is a paper well quoted in the Journal of Knot Theory and Ramifications, 2011 maybe. Okay, on the origin of Gauss linking number. And the demonstration.
So you're saying that you can think of the contribution when the two are crossing one another as a solid angle, a bit of solid angle.
That's
right. And if the diagram is flat in the plane, then you see very clearly that the only contributions are right near the crossings. Otherwise, the cross products are killing it.
Thank you. When you are in the plane, this point goes to infinity and you don't see the sphere anymore, or if you like, you still see the sphere, but as a plane. As a projective plane, if you like, to say it this way. Okay. Yeah.
Renzo,
Yeah.
keep in mind that you could have extra time tomorrow
Okay.
and Friday, so don't worry about finishing this. Take your time.
If I'm too quick for you, tell me. Otherwise, try to follow and questions, etc., will come. But I'll try to stick at that. Okay, here is the minimal projections, as you know, and by deforming this diagram to that one, no change of topology, just no cuts, etc., you do not count self apparent crossings. Okay, this is the assumption. And so if you count just the crossing with the blue and the red, you come up with this. Now we have to consider a knot, not a link. Because for links, we are done with Gauss linking number. For knots, we have this contribution, 1961. I'm sorry, I don't want to boast my knowledge of languages, but I come from a region where French is spoken. I can read very well French. And the paper by Calugariano, it disappeared for many years. It went lost. Why? The paper is totally in French and is published in a Czech mathematical journal. And again, I went through this paper. And to my supervisor, I said, look, we have Calugariano's work. Oh, he was very interested.
So why didn't know about Calugariano?
No, this is another story that is very interesting. I'm glad to share it because at the time, White took the Calugariano's work because of Paul, his supervisor, a mathematician in the US, was very keen to extend, to see if what he could do with Calugariano's work. So White published that paper in '68, and taking Calugariano's work and extending the formula to higher dimensions. That's the only contribution he did. So we believed with Keith Moffat that we had to go back to Calugariano and quote Calugariano. Calugariano is mentioned in White paper. But White, I want to go all the way on this because to make...
But not referenced?
No, reference to Calugariano. But then, listen to this, he had the great luck because of the interest of DNA people, in particular Watson in San Diego. And
Correct. I think you wrote a paper with Crick.
Exactly. And then they wrote a paper that also a popular paper or popular journal, Scientific American. No mentioning of Calugariano. And so people started to attribute this formula to White. And when I told this story to Vaughan Jones, he heard a little bit about this. He said, oh, wow, amazing. He was very, very surprised. White asked us, he's still alive, and there is on record what I'm saying, asked us to provide an apology for this. And we never did, because I took with me the transparency, the photocopy of his first page, published page, where he mentioned Calugariano.
You're saying White asked you to apologize to him?
Yes, yeah.
Oh.
But the story went like, he was also a kind of bad luck. Sometimes, luck is always with us. In the same week, I was giving a talk in Princeton, the Advanced Studies, and Keith gave a talk, totally unrelated, was giving a talk in Bure-sur-Yvette, the center in Paris. Keith Moffat.
Yeah.
So Keith Moffat gave a talk in the same week at Bure-sur-Yvette, at the Institut des Hautes Études, and I was giving a talk at the Institute of Advanced Studies in Princeton. And so we discovered this request of apology too late. Anyway, we never apologized. There's nothing to apologize. Okay, so the proof is entirely in Calugariano's paper. Okay, so I cannot go through the proof. I give you just a visual interpretation of the work of Calogeriano. Imagine that instead of a tubular neighborhood, you consider two neighboring field lines, so to speak, two curves. And these are the two curves. I have a C and a C prime. And as long as the two curves are not overlapping, so they are distinct in space, you can still think of the linking number by Gauss. The two curves are here, the axis and another curve. They are connected through this unit vector. The unit vector refers to a ribbon. So you introduce the concept, the mathematical concept of a ribbon. The first curve is this. The second curve is done by this unit vector, epsilon being the width of the ribbon. And this defines the ribbon. Sometimes it's called ribbon of CC stars. Sometimes it's a C, and the other term refers to the unit vector that is producing the ribbon. So you have a linking number between C and C star well defined. And of course, in terms of epsilon, then you take the limit as epsilon goes to 0. It's really classical analysis. It's a paper on analysis, really. And you get this formula. This formula is just amazing. Why? It's one of the very, very few formulae that in mathematics, in all mathematics, that relate SL in topological quantity with these two quantities, rise and twist, which are purely geometric, global geometric quantities. You know, you have only Gauss-Bonnet on one side, Milnor on the other. Very few instances where you see a connection between the two realms of mathematics. Right, it just gives you information about the coils, the amount of coils of this ribbon. Notice that the formula is identical to the linking number, except that the domain of integration is one line, C, the axis of the tube. Total twist involves a ribbon. It can be split further in two contributions, again, of global geometric character, total torsion of the axis, and the contribution from the ribbon. So if you tight, so to speak, if you keep tense your ribbon, then you have a twist visualized by this. This is all the stuff, and goes back to the age of these people, because I bought a belt from a ladies' shop, and then I wanted the black and white, so I put a tape on it. I had to do, real physics experiments, and so if I do the twist like this, allow me, for the sake of time, to be brief. I keep twist like this. I can convert a twist to the coil. There is a continuous transition from a coil. If I do a coil, you see here, I use this laser pointer, is always pointing toward one direction. So there is basically almost no twist. There is no twist if you go in the limit of very thin ribbon. But then I can deform it and I get a full twist. No torsion if I keep it straight, because the center line is just a straight line. There is no torsion at all. Okay, so this is the decomposition that is very relevant for applications. Okay, here you have your Rider-Master twist move, so to speak, that is frozen there. But remember, it plays a role in physics. Okay, and this is the standard stuff. You project your thing, you go P to infinity, you count the crossings, etc., etc. Now the right, as the linking number admits interpretation in terms of signed crossings, similarly the linking number, similarly the right, because the formal structure of the right is the same, you can do the same, but because it's a global geometric quantity, then it depends on the projections. So to have an exact information about the right, instead of going through the formula, you can count all the crossings that come from all infinite number of projections. And so these brackets denote the average crossing of the average measure of the projections. Another interesting quantity came from Mike Friedman. We were together in California, in Santa Barbara. At a certain point, he said, what about if we take the mod of the numerator? I said, and so what? Well, you count the crossings without any sign. You take, I'm Italian, for Indian people or Chinese, they think of noodles. We take spaghetti, we boil spaghetti, and an exercise that I recommend not to do it with your wife or your husband in house is to throw the spaghetti and take a picture. And if you do this, you count the crossings. You are very happy. Of course, everything has to be cleaned up, but your mathematics is in the lab. And you count the crossings. In each picture, you take several pictures because you are young and you have a very good camera, one of these modern cameras that do all this. And you see that there is the crossings you count because are a way to say, here I am with the strands. Strands carry mass, vorticity, magnetic field. So it's a measure of the energy density that you have. If you have very sparse crossings, maybe the energy is not so much. If you have highly packed number of crossings, maybe the energy is important. Anyway, the same formula, but in this case, you have a mod, so no signs. You count all the crossings. This is neither geometric nor topological, it's algebraic. So here you have a simple example where you have 3 coils. Suppose they are really flat, otherwise not. The right, at least from a vertical direction of flat plane, is -3, but the average crossing number is 3. Similarly here, the right may change because the relative orientation of the coils changes, but the average crossing number is the same. And if you have 2 coils the same sign and the other one opposite sign, then evidently the right or the projected right is also changing. Okay, I told you about work on entanglement. This is much more modern work done in China by Yu Yang and collaborators. It's a fantastic work. And they establish a very well correspondence between the state of turbulence in classical fluid and the skeleton of these vortices in a context of a superfluid. It's an amazing work that draws attention to the importance of skeletons or vortices in superfluids to go back eventually to classical fluids. Okay, and vorticity in superfluids is highly localized. Whereas in classical fluids, the idea that I gave you to think of vorticity in tubes maybe is a mathematical way to think about that. But in superfluid, it's perfect. That's why I tend to pay more attention to superfluids. Okay, this is the energy decayed through decays through reconnection. I just mentioned very briefly reconnection. Feynman noticed that as one of his drawing in one of his lecture notes, and pointing out the fact that you go from, you see the picture, it's a big scale that goes down in scale. And this is typical of the unsolved open problem of classical turbulence. You go from a bigger scale through reconnection to produce smaller and smaller loops. And the lady here has a beautiful t-shirt which shows the reverse cascade. This is a natural cascade, complex structures, too small, unknotted, unlinked loops. But we have also the reverse cascade also in nature. Okay, so this is pictures. These are pictures taken from the movie. I showed you where a strand and another strand at a certain point interact here, and they reconnect and they change topology. As I said, I will talk about this slide tomorrow. And this is what you may say is a standard cascade of topology that you expect from vortex structures. And these these simulations have been done by Simone Zucker with using a Gross-Pitayevsky superfluid code. And with the superfluid code, you see the cascade very well. You can measure helicity. You see total helicity stays almost 0. This is another story. But with contribution of Rife and twist changing through reconnections and through the work. Now I want to, on purpose, I want to draw your attention to 26 years old work that I've done with Carlo Barenghi in Newcastle with the best software available at the time. And we started to simulate a tangle of vortex filaments and superfluids. And we get to this stage. And then we did the measures of what I told you, linking numbers, writings, etc., through exact computation of the integrals, so analytical computations of analytical formula, but also with the crossing count at the time. Okay, and so this is the situation. You project on any plane you like, but then what about the right? I told you that you have to do infinite number of projections. Well, you can do better than that. You can consider, instead of the exact right that you can compute with your formula, you can approximate the exact right by taking 3 mutually orthogonal projections. Just 3. Only 3, and you will see how the two curves basically overlap. And similarly for the crossings. So you see the two curves here, for example, you have a log C bar, and then the projected contribution from 3 orthogonal planes. From the right, we could not show the differences. The two curves were basically the same. And what is the result of this? You consider the mature tangle, you compute helicity, you compute energy, you compute total length of the tangle. Remember, energy goes up because we pump energy in order to produce turbulence. And finally, this is the last slide. We want to relate one of these quantities. They grow in time, similarly to energy. And the result is this, that you can measure energy, if you like, and in terms of helicity, in terms of average crossing number, pure number of crossings that give you a hint. This is just one test case on energy. So you imagine you want energy, you take the square root of the average crossing number, you have information about energy. Everything is non-dimensional, of course. This is the state of the things 25 years ago. Now, next step is to use knot polynomials on tangles, on complex vortex tangles or magnetic stuff. What we have to do, it takes time because we have to teach junior people to project, to know knot theory, to compute knot polynomials from projections. It's a long story. Anyway, thank you very much for your attention.